So last time we were previously we have proved the Cartan decomposition theorem for the algebras, the existence of a Cartan decomposition and the existence of and the uniqueness of it, mod inner automorphisms. And what we wanted to do now is to establish from this multiplicative Cartan decomposition. So in a sense, we wanted to go from this decomposition in the vector space level to a decomposition in the group level, where G is going to denote either the automorphism group or the inner automorphism group of this Lie algebra G. So there are more general versions of this theorem for semi-simple Lie groups, but Onishchik doesn't cover this, so I'll just stick to the case of the automorphism group and the inner automorphism group. But nevertheless, I decided to include in the notes that I'm putting in the web page also the proof for the general case for semi-simple groups with a finite amount of connected components. So what we were doing is we had established in the last session the polar decomposition theorem for non-degenerate matrices. So remember that we have the polar decomposition which essentially means that if you had the orthogonal group and what we defined as P of n, which denoted the symmetric matrices that are positive definite, and S of n, which was the symmetric matrices, then the exponential map was a diffeomorphism between Fn and Pn. And we had the polar decomposition was essentially the multiplication map. So we had proved in last section that this was a diffeomorphism and that this map also was a diffeomorphism, and we computed the explicit inverse by using the exponential map given here. So we were starting off a small detour from Onishchik's book, in which he just goes directly for the automorphism group, and I decided to use another reference, which was the book by Hilbert and Neef, in which they prove the polar decomposition theorem not only for the automorphism group but for any algebraic subgroup of GLNR which was invariant under transposition. So just remember from last session that if you have a subgroup of GLNR, then we said that it's an algebraic subgroup if it was determined by a system of equations, algebraic equations. G is algebraic if it was the solution set of a possibly infinite system of polynomial equations. And the key result that we needed to use was the fact that for diagonalizable matrices in GLNR, then being in the Lie algebra of G was equivalent to the exponential of our elements being in G. So we don't need the whole one parameter subgroup to be contained in G. It suffices to check it just for one value. And this was this lemma that we proved last time. So suppose that G is algebraic. Then if Y is any element of G element, that admits a diagonal basis, and the exponential of Y is in G, then Y is in the Lie algebra. Okay. And you both made extensive use of G being defined by a set of polynomial equations.
Sorry, is there some nice counterexample when it's not algebraic and this doesn't hold? Maybe like with some weird tori or something.
Not that I know of, but I think it would be interesting to think of that.
Yeah, I guess it should be some, like, I don't know, maybe some weird, like, irrational torus in ON or something. Yeah, I think it's important. I was just asking. Maybe you had like a quick example.
No, that I know of, but now I'm interested. So I look for it because maybe it's. I don't remember if they had a counterexample in this book, but I'm sure there's a noun counterexample. But I'll think about it.
Okay. Yeah. Sorry. Okay. Thanks.
No problem.
Okay. So we will combine this result with the polar decomposition theorem to directly obtain a polar decomposition for algebraic subgroups. So you can just So, and the statement is the following. Theorem. So assume that we have an algebraic subgroup of G and R. And we also have to make a further assumption, and it's that G is invariant under transposition. This is not going to be a problem for our setting. And such that G is in G, and this is equivalent to the dual of G being in G. Translation. So we're going to define a K and a P for this subgroup. We will define K to be the set of orthogonal matrices in G. We're going to define capital P as the set of symmetric matrices in the Lie algebra. And we're going to define Gothic P as the capital P is going to be the set of positive definite matrices in the Lie algebra, and Gothic P will denote the set of symmetric endomorphisms in the Lie algebra.
Sorry, is star just transposition?
Sorry?
So G star is just G transposed, right?
Yes, G star is transposed.
Huh?
Because
Okay,
I was using this notation previously for
Yeah.
endomorphisms.
So just to keep the notation exactly the same. So the Lie algebra of this subgroup should be analogous to the K in the Cartan decomposition, and this P should be the P in the Cartan decomposition of G, in a sense. Okay. So then the exponential map gives a diffeomorphism between Gothic P and capital P. And second, the multiplication maps also look like diffeomorphisms. So it's just the restriction of the decomposition map. K and X. K e to the X. And psi to the multiplication maps up. And the same multiplication map that's different from an exponential. To K and X, to K e to the X, then both these maps are diffeomorphisms. And we know that this theorem was true for the whole GLNR, that the exponential map here is a diffeomorphism and these multiplication maps are diffeomorphisms. And since these subgroups are closed and embedded, in reality the only thing that we have to do is to simply check that the exponential sends P to P and the multiplication maps here restrict correctly to G. And accordingly so with the inverse maps. That's the only thing that we have to do for the proof. Okay, so first we check that dimension of P, Gothic P, is capital P. So the right inclusion is obvious because the exponential of any element here, since it's in the Lie algebra of G, its exponential is in the Lie group, and since it's in the I'm using myself. Yeah, here there was a mistake. It should be the mistake. I didn't notice, sorry. So suppose that when you have an element in P, then since it's in the algebra G, then its exponential is in the Lie group G, and since it's a symmetric matrix, then its exponential is a positive definite symmetric matrix. So this right inclusion is obvious. Yeah. Okay, so now we prove the left inclusion. So we have to assume that we have an element in P. So we know that it's the exponential of a unique element, and we need to see that it's in capital in Gothic P. So let's let G include the arbitrary. So remember that the inverse of the exponential map was denoted by log. And this is an element of the algebra, and this is a symmetric matrix. And we need to check that that is in the Lie. That's in the Lie. So this is in satisfies e to the log g. So we have a matrix that is symmetric, so it's diagonalizable, and its exponential is in G. So from the previous lemma, we know that log G must be in the Lie. So since log G and e to the log G is in G, you get log G is in G. And also symmetric matrix is in G as desired. Okay. So this proves the equality, and then the exponential map does restrict to a diffeomorphism. And for the second part, we're going to do it like we did with the case of the polar decomposition for the whole GLNR. We're simply going to prove the result for the second map, the multiplication map involving the exponential. Since these two differ by the exponential of p, that's not going to suppose a restriction. We proved. Also for that. And again, the only thing you have to do is to see that the image of psi is G. That it's not only an inclusion, but it's an equality. So you see psi of k times p is equal. So again, the equation to the right is direct, because if you have an element of this form of a kx with k in k and x in p, e to the x is in capital P, so it's in G, and k is in G, so the image is clearly in G. So we have to see that the left inclusion also holds. Left G. Okay. Then for this explicit map, we had computed the inverse of psi, and I'll briefly recall that this inverse is given by the following expression. So it should be G e to the minus 1/2 of log G star G, and 1/2 of log G star G. And this is why we need to use the fact that the Lie group G is invariant under transposition. So note that since lowercase g is in the Lie group G, then G star is also in G. So since G is an element of G, this means that G star is also in G, and so the product is in G. But the product G star G is also a positive definite operator. So this is an element of P. Okay. And now if we take the logarithm, we know that the logarithm is encoding P. And now this proves that this second term here is indeed contained in P. Now we need to see that this is in K.
Sorry, could you say again, why do we know that the psi of kp equals the whole G? The thing on the left board.
We have to see that this is true. That's what I'm trying to see. What
That's
what
that's
the
what we
expression
want.
to the right. And now what
Yeah,
I'm
yes,
proving
sorry.
is that if you have an element of G, then it must come from an element of K times P.
Okay, cool. Yeah.
That's
Thank you.
Why I was saying that.
Mhm.
This element is G. Okay. And now we need to see that G to the e to the minus 1 log G star G is in K. So proof of this. So this is an element of ON, okay? Because this is the inverse map of the polar decomposition. And this was in G, if I remember. Yeah, because if you think of it, this is essentially the square root of G star G. Okay. Just go a little faster here. No, it makes sense to me. So, I mean, G star G is an element of G. And we know that its logarithm is in the Lie algebra. Okay? So if you take the one parameter subgroup and you evaluate it at -1/2, this must be in the Lie group because it's the corresponding one parameter subgroup evaluated at a value of T. So this is also in G, and then this element is in G. So it's here. But it's also an orthogonal matrix because this map is the inverse of the polar decomposition theorem of the polar decomposition map. So this is an orthogonal matrix.
Why are we calling this expression the big expression, the psi inverse, if we, I mean, is this what we want to be the psi inverse, right? We don't know yet that psi is surjective and covers G as well.
So I don't know if you remember that in the previous session, we proved that this was the inverse in the case of the whole GLN.
Oh, so this psi is the for the whole GLN.
Yes.
Oh, yeah, okay, because we also call him by psi. Oh, I see.
Yeah.
Sorry. Yeah. Now I
I'm
see.
using the same notation. That's why I wanted to keep the notation exactly the same as in the whole general linear group.
Yeah, that makes sense. Thank you.
And this was the map that we derived in the last
Yeah.
set.
Mm-hmm.
So yeah. Okay, so I'll just write it down here for clarity's sake. So this is an element of G intersection ON because G star G is in G. So in particular, log of G star G is into the algebra, and then the exponential 1/2 minus 1/2 log G star G is an liquid, and then G is equal to 1/2 G star G is in G, and it's also in 1. So this was something that we saw in the previous session. So this is complete. So we proved that G comes from the element psi minus 1 of G, and this was in K times P. So this is an equality, and then everything restricts nicely, and then we have the polar decomposition theorem for general algebras. So I don't know if there's any questions now. Explain this wasn't too clear. So far, so good?
I think it looks clear. Yeah.
Okay.
So yeah, and then because we already know everything's a diffeomorphism, the big one. We just need to show the inclusions, right? That's the.
Yeah, because we had proved that this was a diffeomorphism in the general session.
Uh-huh.
When and the symmetric matrix. So, and we're using that everything here is an embedded submanifold of a corresponding embedded manifold. So either the whole GLNR or the product.
Mhm.
And the moment that you prove that you have the restriction the correct restriction, you simply use that everything here are embedded submanifolds, and then the diffeomorphisms restrict correctly.
Yeah, okay. Yeah, maybe I wanted to ask this question. So I remember that kind of a similar statement in Knapp's book is done
Yes.
for like any, I guess, maybe connected semi-simple Lie group, but you start with it's kind of similar in the end, but then you start with a, say, connected semi-simple Lie group with the kind of an involutive automorphism given, and you denote by K the fixed points subgroup, and then you it's proven, and then kind of a similar thing by for P you would have the -1 eigenspace of the differential of that involutive automorphism on the Lie algebra, and then it would be very similar. For the exponential map, you would have the exponential map of the group, but basically the way he does it is by first proving everything in the linear setting by applying the adjoint map. So basically, you replace your group G with the image of the adjoint representation in the GL of the Lie algebra. So basically, you have some subgroup in OT G, which in turn sits in the GLG. And so my question was, so basically, and then he somehow lifts it to the whole group. So he lifts it back to G. So my question was, so here we're doing this for algebraic subgroups of GLNR by using this lemma for diagonalizable matrices. And he does it for, say, images of adjoint of all of like arbitrary semi-simple groups. My question was, how is his statement more general? Is our statement more general, or are they? How big is the overlap? Something like that. Because ours seems more general in that we allow reductive subgroups sometimes. For example, we allow the whole GLNR.
So if I remember correctly, in Knapp's proof, so implicitly he does essentially the same as we do, but it doesn't exactly look like it because, for example, I think Knapp doesn't explicitly give the polar decomposition theorem, but he proves it inside this theorem, because I think you're referring to this giant proposition in Knapp's book where where he gives the existence of capital theta and he proves the Cartan decomposition. But I'd say the
Maybe like my question was that, is it true? I don't recall. Maybe I read it in like Colros, but I forgot. So is it true that semi-simple, let's say, so if you have some connected subgroup of GLNR, let's say it's closed, and then its Lie algebra is semi-simple, so the group is semi-simple, is it automatically algebraic?
Is it automatically algebraic?
Sorry? Because if it is algebraic, then our result is strictly more general than Knapp's.
It would be strictly more general. I'm not sure if there was in one of the articles on community one actions. I think Jürgen mentioned something of this sort, that if G is semi-simple, then it's algebraic under some conditions. I don't know if you know about this. In this article where he talks about the canonical extension. And
I'm not sure it was completely right. We're checking now. But it was a long time ago. But I think there was some theory of most of.
Yeah, that's what I'm thinking.
Yeah. But I don't remember it now, but I can check it if you want.
Yeah, maybe we can look it up for the next time. But basically, if it's true, then it means that then it means that kind of our result covers his, at least in the when it's all inside GLN, when it's like after the adjoint. Yeah.
This thing had to do with the fact that this small thing that happens, that if you have reductive subgroup of a semisimple group is not necessarily a reductive.
And a
It's
reductive
not
group-
the same being reductive
As a Lie group itself.
as a subalgebra.
Yeah.
And being reductive as an algebra, being a subalgebra of a semisimple algebra or something.
Yeah. Yeah. Okay. Yeah. In any case, sorry, that was a
I remember it
digression.
has something to do with that, but I can't recall.
Yeah.
now.
And
Mhm.
also, I think Knapp gave this super general definition of reductive Lie group in the next chapter.
Yeah.
The
Yeah.
advanced structure theory chapter, and he also proved that a much more general version of the Cartan decomposition. So
Okay. Yeah.
I dare to say that the most general version is probably his, but the one in chapter 7.
Yeah. That makes sense.
That's probably
Okay. Yeah. Thank you.
no problem. Okay. So let's keep going. And now we go back to Onishchik. So I think that's everything that I wanted to use about algebraic subgroups, and I'm simply going to apply it to the automorphism group, and everything will essentially come for free now. We go back. In case the automorphism group of G0, where G0 is the real semisimple Lie algebra. So recall that when we had the Cartan decomposition of G0, we had a Cartan involution, and this gave us an inner product on the Lie algebra. And we can again talk about orthogonal homomorphisms, self-adjoint homomorphisms. So it should be theoretically possible to extend this result to particularly the result. So let G be the automorphism U get to 0 and fix a Cartan evolution. And its corresponding Cartan decomposition. So G equals K plus P. Okay. So we had computed in the last session the adjoint morphism of elements in this group and of elements in the inner derivations. So recall that you have alpha an automorphism of G, then its inverse, its adjoint map was given by this conjugation. And also, we had that the dual of the adjoint image of any element of G is the same as minus add of theta x. So essentially, we need to give for this Lie group G, we need to give the K and the two P's. And also note that from this expression, obviously the automorphism group is closed under taking the dual map, because this is the composition of 3 automorphisms. Note that alpha star is in G for alpha in G.
first. Remember, the K from equal decomposition is the orthogonal matrix is here. So this is the set of alpha such that its dual is equal to its inverse. So alpha star, which was equal to theta, alpha minus 1 is theta, is equal to alpha minus 1. So if you look at this is essentially the same as commuting with theta. So that alpha theta and theta alpha are equal. Now, the Lie algebra of G is the adjoint image of G0. I'm going to denote this decoding P for a moment as P tilde because we already have the P from the Cartan decomposition, but they're going to be related by add. P tilde is going to be the set of all elements in at G0 that are symmetric. So this can be written equivalently as the set of elements of the form at X such that minus R of theta X equals R X. This is the same because R is injected as the set of elements of the form at X such that theta X is equal to minus X. So this is the adjoint image of P. So they are identified by the adjoint representation, which was an isomorphism into its image. So note that for construction, K is compact, and we can also give its Lie algebra. So I'm going to note like K here. So K tilde is the set of elements in at G0 whose corresponding one parameter subgroup is in K. This is each of the beta is in K for MOT now. So we're going to try to understand this condition in terms of commuting with theta. This is the set of elements of the form X such that e to the t of X commutes with theta. I think this correctly. This is all. If we differentiate this at 0, this gives us at X with theta, and if we differentiate this at 0, we get theta of at X. It's the at X such that at X theta is equal to theta at X. Okay. If you remember conjugation by theta, if you take the conjugation of at X by theta, this is the same as at of theta X.
So this is the set of all elements of the group at x, such that at of theta x is equal to x. So essentially this is equivalent because I is injected to theta of x being equal to x. And this gives us that the Lie algebra of the compact group K is R of K. So the vector subspaces in the Cartan decomposition of the automorphism group are precisely the adjoint images of the summons in the Cartan decomposition of G0. And now with this in mind, the only thing we have to do is to simply rewrite the polar decomposition theorem, but changing the names accordingly so that it corresponds to the automorphism group. Theorem. Saying that Cartan decomposition theorem for the groups. So let's try to write it in full generality. So let G0 be real semisimple. Theta Cartan inclusion. And let K and P be given as here. So K to be the set of all automorphisms that commute with theta. P to be the positive definite elements of B0 and Gothic P to be equal we don't need to define the Gothic P because we are writing by path, so we can skip defining it again. Okay. And first, K is compact with the algebra at K. Or equivalently, you can say it directly as K. First, back to this theorem. Second, the map that takes elements of T and takes the exponential of their adjoint representation. So E to the f x. This is a decomorphism. Just a composition with the exponential map for symmetric matrices with the adjoint representation, which was already a linear isomorphism. And third, the multiplication maps take K to KP
and taking K times the vector subspace P. What is 0? Into X. K exponential of X and diffeomorphisms. And this is what we proved. So again, everything came directly from proving the more general result for algebraic subgroups and simply interpreting the conditions that we have for the automorphism. And now we're going to simply see how these two maps restrict to the inner automorphism group, and it's just a topological argument. It's very simple, and this will give us the Cartan decomposition for the inner automorphism group. We simply have to notice that since these are diffeomorphisms, they preserve connected components. And since we are in the semisimple case, the inner automorphisms give the full identity component of the automorphism group. We can write this as a corollary. States that first, if we take the connected component containing the identity of K, then this can be seen as K intersect the inner automorphism group of this one. And it's almost obvious because note that P is a vector space, so it's simply connected, and the identity component of K is K0, so the identity component of this is K0 times P, and the identity component of odd G0 is the inner automorphism group of G0. So there's almost nothing. So since psi is diffeomorphism, it preserves components. So psi of K0 times P, which is the connected component containing 1, 0, has to be equal to the connected component, the identity. And similarly for the map phi. Similarly, we have that K0 times P is equal to the automorphism. So in other words, the inner automorphism group is the product of K0 and P. And this means that for an element to be in K0, it must be here and it must have a 0 part in P. So this means that K0 is the intersection of K with the inner automorphism group. And again, now from here, have the corresponding Cartan decompositions for the inner automorphism group, which I'll simply write as this way. The maps by let's say K0 times P. So the inner automorphism group G0 and psi takes the K0 times capital P. These are also diffeomorphisms.
So I think this is everything that I wanted to talk about. As for establishing multiplicative decompositions for the automorphism group. And from now on, the remainder of this chapter is essentially devoted to seeing that K and K0 are maximal compact subgroups of the automorphism group and the inner automorphism group, and to see how they are in reality unique up to conjugation by an element of the group. So I have time. I have plenty of time, so I'll start by proving this maximality. It's going to be very simple from the multiplicative decomposition, and then I'll try to start giving a sketch of why they must be unique. This is the last section. So we keep the notation from that have been using, so that's 0, be real semi-simple. So we have our K. Maps. We have P. Intersect the positive definite. The positive definite maps into 0, and we now know that it's also the exponential image of a P. And we have K0, that it's the identity component. So firstly, we will see that this is maximal compact in the automorphism group, and this is maximal compact in the inner automorphism group. Right, to test up the theorem. K is maximal compact. In the automorphism group. And K0 is maximal compact in the automorphism group, in the inner section. And we simply use the Cartan decomposition. So suppose that I'm just going to prove it for K. The proof for K0 is exactly the same, replacing the automorphism group with the inner automorphism group. So you'll see why in a second. So suppose that L is another compact subgroup that contains K. Okay, so let L be compact. And such that K is contained in L. So if K is strictly contained in L, then we can use the Cartan decomposition to find an element of L that is also in P. So if K is not equal to L, then we know that from the Cartan decomposition, the automorphism group we directly deduce that L must be equal
to L intersect K, L intersect P. But since K is in L, this is simply L times L intersect P. And this second factor is not trivial. So this should be K. This is in terms of the number. The second factor should not be trivial. Okay. Now take any element P in L intersect P. So essentially we can now take powers of P and these are they are going to stay in this intersection. But these powers are going to have increasing norm and they're going to give an unbounded sequence of elements in L. So it's clearer to see it in terms of the logarithm. So we can consider the sequence. So e to the I is in N. And if we take logarithms, this is essentially I times the logarithm of P. So since the logarithm Pi is equal to I times the logarithm of P, and this goes to infinity as I goes to infinity, well, in norm it goes to infinity. This means that this sequence is unbounded and therefore L cannot be compact. Is unbounded. This is another contradiction with our assumption that L is a compact subset. Okay. And again, the proof is exactly the same when replacing K by K0 and the automorphisms with the endomorphisms. So as for K being maximal compact, Onishchik gives a sort of analytic proof. And there's also a well-known proof of this fact using the Cartan fixed point theorem. So maybe you're all familiar with this. The usual proof goes along these lines. So, a possible proof of conjugacy. Essentially, what you would have is that if you take the quotient d mod k, then this is a Riemannian symmetric space of non-compact type. So in particular, it's a Hadamard manifold. Space. Where G acts by isometries on G mod K for a certain invariant metric that is adequately chosen. So it's well known that these are Hadamard manifolds, and therefore the Cartan fixed point theorem applies here. The proof should go as follows. So suppose that you have any compact subgroup of G, let L be a compact subgroup. Then, since L acts by isometries on this symmetric space, it means that it should have fixed point because of the Cartan fixed point theorem. So, by preference. In theory, we know that L must fix a point of the type of the sort of, let's call it GK. Okay. And the isotropy subgroup of GK it's well known that the isotropy subgroup is obtained by conjugating by G. So more precisely, we should have that L it fixes GK, so it's contained in the isotopy subgroup of GK, and this is GK dimension. And this would prove the conjugacy of maximal compact subgroups, essentially. So we need to know the Cartan fixed point theorem. We need to check that this is a Riemann symmetric space of non-compact type. But this is the most common geometric proof. Just to give a short argument about why what we're going to do next is true. So now I'm going to talk a little bit about how the proof by Onishchik goes, and maybe start giving some details, but the bulk of the proof will be, I prefer to do it in the next session to have more time for this. Okay. Okay, so sketch of proof by Onishchik. So we will define an action of the automorphism group on, and it's simply an action by change of places. Okay, so it takes alpha and p to alpha p alpha star, where alpha is any element of G and p is any element of P. Okay. So note that this action is transitive, and this is basically because every element has a square root. So this action is transitive. Because P is P, then you can write P to be equal to P to the 1/2 times P to the 1/2, and this is the action P to the 1/2 E. So this is a transitive action, and this allows us to realize the space P as the quotient of G mod K, or as the quotient of the inner automorphism group mod K0. And we need to see that this action fixes a point, but we are not able to use the Cartan fixed point theorem for this. The idea is that every compact subgroup of G fixes a point. And by essentially this argument, we see that if L fixes a point, then it must be contained in a conjugate of K. So some. And how do we find this? We will try to find, we will define a function that is invariant under L, and we will prove that this has a unique minimum, and this minimum must be L invariant. Okay. So we find it as the minimum of a certain L invariant function and this will be essentially what we will do for the next session. I think better stop here because what's going to come now is a lot of technical lemmas. I think it's better to just try to do everything at once in one session.